Good morning. Today we're going to walk through a discussion of doing fatigable welds using DesignLife and look at some of the new features that were added at 12.1. Briefly kind of go over just the nCode product range in general. DesignLife is one of 4 products that we have. The other products are nCode GlyphWorks, which actually is used to do data processing for durability. It's able to go in and deal with large amounts of test data and graphically process that to get useful information out of it in terms of the input. There's another product called VibeSys that actually is new to version 12 that actually goes off and allows us to start looking at noise and vibration, as well as looking at things such as rotating machinery and structural dynamics and human perception. Lastly, there's automation, which is a web-based system for data management, primarily looking at measured data, allowing you not only to manage this data, but also process it automatically through the import or export of it. What we're focusing in on today, though, is DesignLife. And DesignLife is basically a CAE-based system for doing durability analysis. It uses results from FE analyses to go in and develop load and then stress histories, allow us to do fatigue. It has a wide range of capability in terms of different fatigue capabilities: stress life, strain life, composites, high temperature. It also has unique capabilities for things such as welds, which we're going to focus in on today. Its input is from, again, leading FE analysis packages such as ANSYS, Abacus, OptiStruct, Nastran. And again, besides having standard procedures for looking at material fatigue, it has very specialized techniques that allow us to go off and look at things in the frequency domain in terms of vibration, allow us to look at composites, high temperature, adhesive bonds. It is highly configurable, such that an expert user can go in and derive it to do the style of analysis he wants. However, it also lends itself to being configured and made able to be presented to casual users, much in the way of knowledge capture and building standard processes. Again, being a C-based system, its major purpose is to go in and not to basically eliminate physical tests, but to go in and allow us to go in and analyze tests up front and make sure that by the time we get to a testing phase, the design is there only for validation, not for going off and trying to identify problems. And again, once we have a system like this, we can go off and actually design our tests to be smarter, faster, and it allows us to go in and take our designs and improve them. A historical way of designing for fatigue was just to make parts heavier, just make it stronger. And in the age of lightweighting, that's really no longer effective. And so DesignLife allows us to go in and be more precise on our fatigue analyses to allow us to go in and to design parts that will be durable, yet allow us to go off and make them cheaper, lighter. And finally, as I had mentioned, it is very much process-oriented, and it lends itself to standardization. So once a process has been developed, you have repeatability and actually standardization across an engineering group. Okay, so today we're going to look at DesignLife in terms of looking at welds. And I'm going to walk through just an overview of fatigable welds, and then we'll look at some of the approaches for doing analysis for weld fatigue. We're going to then focus in on structural stresses and look at some of the aspects that we need in terms of structural stress analysis to do fatigue, and then finally focus in on how we do that for shell modeled structures as well as solid model structures. Then I'll open up for questions. So in terms of an overview fatigue of welds, the first aspect is just looking at how complex a weld is. Obviously, welds are very useful in tying parts together, joining parts, but once we've done that, it becomes difficult to analyze because of a variety of features. When we welded two parts together, we've actually transformed the parent metal that we were welding. We've basically created a heat-affected zone. We may have deposited a weld metal. We've left discontinuities, things like at the weld toe, possibly at the weld root. We've left, many times, high residual stresses. And these all basically build up to make the analysis of the weld far more difficult in a traditional sense. In terms of geometry, if we go off and start looking at things such as the weld toe here of this basically unimproved weld, you'll see not only is it very complex, but we're already looking at things such as crack initiators existing before we even start loading. Another aspect with welded structures is that typically, if I look at the fatigue performance of various grades of alloys, I see a large range in fatigue performance. The higher monotonic strength or tensile strength of a material tends to also indicate that it's going to have much better fatigue properties. When I look at the fatigue properties of these alloys welded together, all of a sudden we see that the welds behave very, very similarly. So once we've welded alloys of different strengths together, their welds act almost uniformly. And what we're looking at here is, this happens to be spot welds, but MIG welds are similar. If I looked at the parent metal, I have variations in here from 280 to almost 1,300 megapascals in terms of UTS, and their fatigue performance all sits in one scatter band. This basically starts to make things like lightweighting more difficult, obviously, because just going off and replacing a steel with a higher strength steel doesn't necessarily improve the performance, especially at the welds. So just some basic observations on welds. Probably the critical one is that the fatigue properties of the welded structure are completely different than those of the parent metal that we've welded. And this is due to a variety of reasons, and one, again, goes back to looking at the weld toe, where we have very sharp, we have ill-controlled geometric features, large stress concentrators, even existing crack initiation sites. We can have defects in the weld as well, things like slag inclusions that may be failure locations. We have left very high tensile stresses, residual tensile stresses in the part, and that has issues in that now any cycle that I apply to that structure, every cycle is damaging. All the cycles become tensile. We have a non-uniform material distribution. Again, once I've welded this, I have generated a heat-affected zone, I have deposited weld metal, and I do not have a good definition of where those boundaries are. Finally, the last couple items. One, we'll see, and I think primarily because of the discontinuity in the geometry and the initiation sites, fatigue behavior of welds is primarily crack growth. If we look at the slopes of the SN curves and look at the behavior, they basically follow crack growth behavior. Again, the fatigue properties of the welds tend to be much lower than the fatigue properties of the parent metal that was welded. And then finally, again, that if we look at the behavior of welds across a wide range of alloys, the weld behavior, the fatigue behavior of those welds is very similar. with that said, we have to look for approaches to go off and analyze welds for fatigue. And there are several that we can look at, one being crack growth. I had mentioned that welds behave primarily in crack growth. Issue with crack growth is, one, it's a very point-wise solution, and it's very sensitive to the starting points. So basically, the initial crack size, crack shape, direction, all have a huge impact on the final answer. Also, the crack growth rate is a function of the crack size, such that we can't go off and leverage things like Miner's rule. We actually have to solve this iteratively to failure. So, though it would be the ideal approach for looking at the behavior of the welds, it's not really ideal for applying it to a whole structure and a large portion. Another approach is going off and having some sort of local modeling of the welds. And here, either we will have a refined mesh around the weld itself, maybe in our model, or we will have breakout models that go in and describe the detailed weld behavior and geometry from maybe information from a course model, things such as displacements or forces. This has some benefits in that we're able to go in and more closely describe the weld geometry and things such as the weld reinforcements, the penetration amount, but typically when we look at these, they tend to be very much looking at a cross-section of weld. They don't have applicability typically to things like weld ends, where we normally see issues. So there's a third approach, a structural stress approach, and that's actually what we'll be looking at today. And here we're going to go in and attempt to measure stresses going into our weld and use those as a damage measure to pair along with what we'll see as a component SN curve. And there's a variety of these structural stress methods. We'll kind of go through these quickly: the nominal stress, hotspot stress, nodal force stress, and through thickness integration. These all have the goal of trying to measure the load going through the weld in something that is kind of normalized, hence a stress, yet eliminate the discontinuities at the weld toe. And the initial one is a nominal stress method, one of the earliest, and probably originally it was a strain gauge at the toe of the weld. But here what we're looking at is trying to measure stress at some distance from the weld toe, and ideally picking up a stress that isn't the discontinuity at the weld toe. One issue with this is that it tends to be quite mesh sensitive, obviously, if we're going off and applying this on an FE model. An improvement to this is what's known as the hotspot stress. And here, instead of looking at a single location adjacent to the weld toe, they look at two locations away from the weld toe and kind of linearize or extrapolate the stress to the weld toe location. Again, what we're looking to do is be able to pick up stresses not influenced by the weld itself, yet use those to predict what's happening at the weld toe if the weld toe was not there. This actually is used by quite a few weld design codes. It is relatively labor-intensive to do this in FE, because again, I would need to have specific stress recovery locations typically at the locations that I'm sampling. And again, it's only going to give us stresses at the weld toe. It doesn't tell us exactly what caused the stress, which you'll see is important later. A third approach that is popular is looking at structural stresses calculated by nodal forces. Here, trying to invoke things like equilibrium, what we'll do is take the forces and moments along a line at the weld from the node points that are in the FE model and use those with simple stress calculations, things such as P over A, MC over I, to calculate, again, a stress at the weld toe location that is independent of the weld toe geometry. One of the benefits this method has is that we're able to very easily go in and not only describe the stress at the critical location, but we're able to go in and describe what kind of loading caused that stress. The final and fourth approach that we're going to be looking at today is through thickness integration, or linearization of the stresses. And here what we're going to do is actually have the true stress profile through the thickness at the weld toe. And we're going to go in and use that profile and linearize it. Again, the goal for this is to go off and predict a stress at the weld toe without the weld toe being there. So we're removing the nonlinearity at the weld toe and looking only at the structural stress. And again, this approach, like the null force approach, gives us not only the stress at the critical location, but gives us basically information about the bending ratio or what kind of loading has caused the stresses. Now, when we go off and use these style of approaches, what we're physically doing is taking the fatigue process map, and we're going to go in, and typically the fatigue process map goes off and says what we actually have is detailed geometry of our part, a very accurate finite model describing all the stress or strain information of our part. And we have very detailed material properties for that material to predict fatigue. And again, when we're looking at welds, we have neither of those. We really don't know the geometry, and if we did, we couldn't even afford to measure it to the refinement we would need, and we really don't have the material properties. And so what we're going to do is, in a structural stress approach, we're going to go off and combine those two inputs together. We're going to go in and not look at material, we're going to look at components. So our process map now, we're going to go in and actually build a component SN curve to use in the analysis. This likens back to 150 years ago when that's actually how analysis was done. When Wooler was looking at his railroad axle, he didn't have an SN curve that was ductile iron. He had an SN curve that actually was his axle. It was not only the material properties, but it was the geometry of the axle, surface finish, stress risers. That curve was not a material, it was his actual component. That's what we're going to do in the structural stress method with welds. We're going to go off and test geometries, and what we're looking to do is characterize the weld, not the heat affected zone, not the weld metal. So we're going to go back in and basically treat this as a component SN curve. The process to do that is to, again, go off and have a variety of test specimens, and you test those in the lab, and what you get out of the test specimens are load life curves. Now, because typically these specimens have different geometries, different thicknesses, the load life curves have a huge scatter because some specimens are stronger than others. And what we're going to do is use the structural stresses to actually try to collapse these down to a single behavior if we can. What we do is we take the test specimens that we've tested in the lab and we build finite element models of those, and we use whatever structural stress approach, recovery approach, to get stresses out of the loads. And if we have an appropriate structural stress with appropriate corrections, many times we're able to actually collapse the load life curves to a single weld behavior. Now, this has some issues. The curve that we've created is actually describing the weld. And if we look at the weld, it's describing the weld, and it's using a stress value that's much, much lower than the actual stress at the toe of the weld. That means that baked into that SN curve that we're going to create is the stress concentration factor, the stress concentration factor at the weld toe. And if you look at stress concentration factors, they're not only a function of the geometry, they're a function of the loading mode. So what I have here are basically just two stress concentration factors for the same geometry but different styles of loading, and we end up with different KTs. So what this means is somehow when we generate these SN curves, we have to basically be aware of what generated that structural stress in terms of loading in order to use it properly. There's a couple ways to do this. The classic way that you'll see in use with a lot of weld design codes such as the IIW or the British Weld Standard, the Euro Code, is that they'll go in and have what they call the classification process. They'll go in and look at the part geometry, the weld geometry, how it's loaded, where it's going to fail, and going through this classification, they then point you to a specific, not a single curve, but a family of curves, each one of them for a different geometry, different loading mode, and then a way to recover stresses off that weld geometry. So what I have here is basically the weld curves from the British Weld Standard, but again, if you look at almost any standard, you'll see that you have a whole family of curves, and you go through this classification process that's not only part and weld geometry, but also loading to pick the proper curve. One of the recovery methods that you'll see actually is relatively popular now for this method is the hotspot stress. And something that was just added in 12.1 for DesignLife is a way to actually recover the hotspot stress for these codes. Again, I had mentioned historically, this was basically 2 strain gauges in front of the weld toe, and it has been very labor-intensive to go off and do it using a finite element model because I needed to have very specific either node or element centroidal locations to do this. What we've done inside DesignLife at 12.1 is we leverage what we've done in solid seam weld, which we'll talk about in a bit, but that approach allows us to go in and to use a weld configuration file to describe where we want to look. However, we don't have to match the mesh with the locations we're looking. So the locations for these recovery points are totally independent of either the node or element centroids. So we're going to use that weld configuration, and we're going to go in and identify the reference points in front of the weld toe, recover the stresses from the FE model at those locations, and then extrapolate them up. And again, what we're looking to do is basically identify a stress that would be the stress at the weld toe without the weld toe being there. So the blue trace you see in the lower corner is what we're actually extrapolating. The red would be an estimate of what the actual surface stress is on the real part, and we see that we have a huge stress riser because of the weld toe. What we've built into DesignLife supports basically the IIW standards that allows us to go in and to do either what they call type A or type B cracks, but what that means is either the locations are a function of the thickness of the plate or are actual physical distances, and you can select between that. We also handle both the 2-point and 3-point extrapolation, so a linear extrapolation or a parabolic extrapolation automatically in DesignLife. And there are also corrections there for coarse and fine mesh. These are all following the IIW standard. In addition, it's been expanded such that we can go in and have a user specify locations, either ratio or physical distances, to go in and follow other standards. So the input to this would be a finite element model you see on the bottom where we have our weld, and you can see the weld toe has a very high stress riser. What we've done is defined, in this case, about 100 locations around the perimeter of the weld to do this hotspot calculation. And DesignLife automatically goes in, generates the hotspot stresses for that, and allows you to use that in an SN calculation to predict the fatigue behavior. And what you're seeing in the top display is actually our post-processing of the in this case, the max stress, but again, we pull out things such as life and damage as well for the weld. The markers that you see actually, their large end is the location we're doing the calculation, and they actually they extend out, showing you the linearization path that was used. Now, one way to account for loading mode is, again, to manually go through, classify your model, and select specific curves out of a weld code. there's also ways that we can go in and kind of automatically account for the loading condition. And we're going to look at that. And here, when we have a stress recovery approach that allows us to go in and calculate not only the hotspot stress, but maybe the stress below at the opposite surface or the bending ratio, we're able to go in and to take those stresses and compute basically how much of the stress is caused by a tension load and how much of that stress is caused by a bending load. In terms of shells, it's trivial. If I have a shell model, which we're showing here, I basically can go off and interrogate the top surface and bottom surface. And once I have those surface stresses, it's trivial to go in and calculate what the bending and tension stresses are. And from that, I can calculate a bending ratio. And so the input to our fatigue calculation from a structural stress with an automatic correction is going to be basically the stress at the key location, the critical location we're going to do the analysis at, and this bending ratio. And what's done in DesignLife is we basically take that bending ratio history and calculate an effective bending ratio from it. So this is going to be basically at every node or every location that we're going to do the calculation for the welds. We're going to calculate this bending ratio, this effective bending ratio, and built into DesignLife, we can take that bending ratio and basically generate an interpolation factor. What this is going to be is basically a factor that allows us to go off and interpolate between two curves. One fatigue curve per weld where the weld is completely in tension, tensile stress. A second fatigue curve where the weld is completely in bending stress, which are basically the two boundaries that would be the behavior. And then we generate automatically in DesignLife what is an interpolated curve between those two that matches the bending ratio for the location we're doing the calculation. Again, we're allowing us to account for the fact that different loading modes will generate basically just different SN curves because the SN curves have the stress concentrations of the weld toes built into them. So the approaches inside DesignLife to automatically do analysis are basically using structural stress methods, both in shells and solids. In terms of shell models, what we have is an approach that uses what I consider to be a light modeling of the weld. It's basically the structure is modeled as mid-surfaces, shells, and the weld itself is nothing more than a single shell connection between the two components, basically trying to model between weld toe to weld toe. So this basic weld element here, or the green elements you see here, are the weld itself, and they're really nothing more than a connector between the two components. We're not trying to go off and model any sort of detail in the weld, the radii at the toe or any sort of detailed information about the weld bead itself. What we're going to do is import to DesignLife the elements that represent the weld, and then DesignLife will automatically find all the connected elements. And it's those connected elements that we're going to do the fatigue calculation on. So if you look in the right-hand side, it's the elements that are highlighted in red and blue that are going to be identified by DesignLife automatically. We're going to basically take and calculate, use their information, in this case nodal force and moment information, to calculate structural stresses and do the fatigue calculation. With shells, historically, we've made the user go off and kind of categorize the geometry of the weld. And we had two major categories, one called Fillit, where the components were primarily perpendicular to each other, and the other called overlap, where they were relatively parallel. And the purpose for this was the fact that we're going to go in and look for specific failure locations, and those failure locations are where we end up having sharp re-entrant corners. And so those locations actually change between these two configurations. As you can see, if you come up here and look at the fillet, it's on the right-hand side of the upper toe is where we're doing a calculation for a fillet weld. When we go in and look at that configuration in terms of overlap, that location now is no longer a hot spot for stress. It's basically transferred to the other surface of the shell. And so we we basically identify these locations by configuring the welds as you created those. And again, we're looking at configurations of the shell mesh in the lower panels. You can see that we have different mesh configurations that you can use, single leg, double leg configurations of the welds that we'll automatically understand. One thing we've done with 12.1 is we've generated a new configuration, and this is called combined fillet and overlap. And so this configuration will actually look at the geometry, the angles between the plates that we're welding, and use those angles to decide whether it's a fillet, whether it's an overlap, or whether basically it's kind of in this border between where we can't really easily describe it. So if you use the combined fillet and overlap, you would basically just throw all your welds into that group. And then as we go off and analyze each weld, we interrogate what the angles are between the attached shells that are being welded. And the user has the ability to go in and basically specify a series of angles. One angle that's basically the threshold between something that's 100% fillet and then something that's kind of in between, as we see here, this A2 configuration. And then a second angle is between this intermediate configuration and the overlap. And so the program will automatically go in, and the weld configurations that are basically a fillet weld, we solve the fillet weld. Those that are obviously overlap will be solved as an overlap, and those that are kind of in the intermediate range will be solved for both. And so we'll give you both configurations, give you worst case. And again, this actually, for large structures, will be reduces the amount of modeling effort significantly, because now we don't have to even try to group our welds into one or the other. For shell models, what DesignLife is using as the primary damage mechanism is a structural stress that's calculated from the nodal forces. So when we look at the welds being analyzed, we find the attached elements and basically collect the nodal forces of those elements along the weld toe or weld root. This allows us to go off and calculate, again, a structural stress, which is nothing more than basically simply a P over A, MC over I calculation that would be representative of the load going into the weld. One of the benefits of this approach on a shell model is that I can immediately not only get the structural stress, but I can get the bending ratio, which is important to go off and do the corrections on our SN curve. So again, what would be a model is a shell mesh. The green elements represent the welds that would be identified to DesignLife, and DesignLife would go off and find the attached elements. In this case, this is look at the lower toe where we have elements 5 through 8. It not only finds those elements, it also identifies the edges along the weld toe from those elements, collects the forces and moments from those elements at those edges, and then basically averages them and resolves them to coordinate systems that represent the weld toe. And it's those basically line forces and moments that are used in a calculation of a structural stress. The whole purpose of this approach is to go in and have a stress quantity that is relatively insensitive to the mesh. So I could change the mesh refinement and get very, very similar structural stresses, where if I was looking at a classical stress recovery from a finite element, it would change radically. So this gives us a mechanism to go off and to get a damage measure that's pretty much mesh insensitive, and then we have built into DesignLife this process that takes that and calculates a fatigue for welds. This is the process. It's kind of messy, but if you were to look at the bottom path, what we're doing is taking basically the structural stresses from a particular attached weld, and from that we generate a weld basically a structural stress history at the weld toe where we're going to analyze. We also take that and we basically correct it for things such as thickness, possibly mean stress corrections if necessary. So now we have a stress history where we're interested in doing the calculation. The top path is taking and calculating the stress at the opposite surface of the plate. So if we were saying that the top surface of our shell was the weld location we're going to analyze, we're now looking at the stresses at the bottom surface in the same directions, and using that to calculate this bending ratio that we then go in and use to compute an SN curve to go along with this particular weld location and stress history. That happens automatically under the covers, but what it allows us to do is have basically a single definition of material behavior for welds and steel, one for welds and aluminum. So it makes the system very, very automated in terms of doing analysis. So what we're looking at here is just a simple process for doing welds and shells. If I look at the upper left-hand corner, it's the weld that's actually colored cyan that's actually being presented to DesignLife as the weld. In this case, this was put in as a combined fillet and overlap, so I didn't have to try to go off and characterize the weld that way. And what DesignLife automatically does is at every location that's a connection to it, root, toes, it goes off, characterizes the weld configuration now. It goes off, calculates the structural stresses, calculates the bending ratio, generates a SN curve for that particular loading type, and we'll do a fatigue calculation. And again, what comes out of this is not only the life or damage, but things such as the max structural stresses used in the calculation, actual max and min, bending ratios, configuration type. So this all comes out as results to you. There's also an approach that we can use solid modeling. And so what we have here is the red, cyan, and purple represent kind of a mid-surface shell mesh that I might represent a weld with. And the gray is a solid mesh that could be representative of the same structure. And what we want to do is use a solid mesh in this calculation. Now, again, what we're going to need to do is calculate structural stresses from that. And in the case of solids, it's even more challenging because the solids have even a much larger stress concentration factor, things like the weld toe, because of the rear corner. Here, the structural stress approach we're going to use is called through thickness integration. So we're going to actually calculate through a location where we're going to say the crack's going to grow, the actual stress is calculated by the final element model. And then through that stress profile, we're going to linearize it. And the idea of the linearization is, one, to give me a stress at a critical location that would be the stress there if the weld toe stress concentration wasn't. And two, this approach also gives me the ability to calculate the bending ratio. So again, I can make my corrections automatically. The approach we're using is one out of the ASME boiler code. So it's a linearization technique described in there. And so what we do is we specify a starting location at the model. And that would be a location at the weld where we want to do the analysis. And we drill down through that plate where the weld's going to crack through, and at a given number of user-specified locations, we recover the stresses at those locations, the 2D stress tensors, and we use those for linearization. Key here is those locations do not need to be nodes, do not need to be element centroids. These locations are completely independent of the mesh. So it allows me the ability to go off and map mesh, free mesh, whatever I want to do to describe that. The reason we go through this process can be seen with the sample geometry here. What I have is the same geometry representing a weld where I have a weld here connecting my vertical and my horizontal plate the top of the vertical plate and the back side of the horizontal plate are constrained, and we have a load on the front of the horizontal plate. And we have the same model meshed in the upper left-hand corner with hex 20s, upper right-hand corner with hex 8s, lower left-hand corner as coarse tet 10s, and the lower right-hand corner as fine tet 10s. Same geometry, just different meshes and different element configurations. If I were to go in and analyze this, which we have, in a fine element package, and look at the stresses coming directly out of these models directly from the fine element mesh, I would see that at the critical location, I have variations in that stress from 133, 142, 170, and 252. So it's almost a factor of 2 difference in stress recovery looking at the fine element mesh. If I take and do a linearization of these models and recover the linearized stress, you'll see that the linearized stress, the structural stress through thickness integration, is 117, 117, 109, and 115. We're able to go in and to calculate a stress quantity, again, a damage measure that is pretty much mesh insensitive. It's going to be invariant of the mesh type and density that we have, and allow us to have different meshing configurations used to do this weld calculation. The only really requirement I have on the mesh is that I have at least 3 elements through the thickness where we do the integration. And once we've done the integration, what we end up with now is basically a top and bottom stress on the solid portion of our weld that we use in the same fatigue path that we use for shells. The weld definition inside DesignLife for the solid welds is actually a file that describes locations where I want to do this calculation, and then directions where the weld path is going to proceed. And so at every location we would have basically a physical location in space. And again, this is not a node, this is not an element, it's independent of that. It's just basically pure geometry. And then we have 2 vectors that basically orient the weld. One, so we know how to drill through the part, and second, that it's going to basically give us a direction of the weld toe. This file actually has to be created outside of DesignLife. However, we have currently 3 different utilities, one for Hypermesh, one for ANSYS Workbench, and one for Abacus CAE, that allow you to go in and pick the geometry features in the fine element model and use basically selections of curves and surfaces to basically identify this weld configuration. It's this file that's used in the solid weld calculation, and it's also this file that's actually used for that hotspot stress recovery that I talked about when we were looking at the using weld design codes. So basically, we just go in and literally pick off the geometry inside of Hypermesh or inside of Abacus or Workbench, select curves and surfaces, and then specify how many locations we want to analyze around that path. And what's going to happen is we will go in and do the stress linearization through that path specified at these locations, through that path specified by the configuration file, and calculate the fatigue, damage, life, stresses all around the perimeter. Again, this could be the weld toes, roots, what have you. Here what I have is a very simple model. Now, one thing I'm showing here is because we're actually calculating locations that aren't nodes, aren't elements, we really can't contour. And so we've basically placed markers in the model. Each marker basically represents the starting location where I'm doing my calculation, and then its path shows the path we did the linearization through. And again, these could be contoured based on fatigue, life, damage, max stress, bedding ratio, whatever I want. And so again, the procedure that one goes off and looks at looks very, very similar to the shell procedure. Numerically, once we have the structural stresses, it's identical. The difference here, instead of identifying elements of the welds, we're basically bringing in this configuration file that describes the path around locations where I want to do the calculations. And then at every one of those paths, DesignLife will calculate the fatigue at the weld toe, weld root, and give us life and damage. In fact, actually, both approaches, the stress linearization, the through thickness integration, and the nodal force moment approach gives us very, very similar structural stresses. So we're using the same weld curves for steel and for aluminum. Finally, just as a note, we've already talked about this, but there's been a variety of things that were added at 12.1 for welds. And we've already talked about the hotspot extrapolation. That's the approach where I can go in, use the solid weld configuration file, but do the IIW hotspot weld without having mesh nodes or elements at the stress recovery locations. And again, historically, that approach has been very labor intensive. Now, with this, we can go off, basically, independent of the mesh, be able to go off and calculate this hotspot stress and then use it for whatever weld curve we want. And again, built into DesignLife are things such as the British 7608 Eurocode, or you could basically just import weld curves from other design codes as well. Again, we've taken the shell mesh approach and we've created a new weld configuration that basically combines fillet and overlap that eliminates the need for the user to go off and do these classifications directly. So we can basically just throw all the welds at DesignLife, and it can geometrically now configure them for you. Two things I did not talk about, but just kind of mention, on the seam weld approach, we basically opened up the ability to use the vibration load provider. Historically, seam weld could use any time-based load provider, time step, time series, constant. But at 12.1, we've introduced the ability to bring in basically loading that's either PSD or swept sign based and use that in the weld calculation. Currently, that's shell mesh only, but it's being enhanced at 13 for B general. And then finally, there is other weld configurations that occasionally we use. One of them was generic, and generic basically just took every possible location and solved it. One of the things, it had not been enhanced to use the latest stress recovery, the grid point force method, and mid-edge options, and that's been basically added to generic. And the reason for that is the generic weld actually is very advantageous for doing things like butt welds, where I have here a butt weld between two components, and really what I want to do is look at every toe. And so the generic is ideal for doing that. And so we've enhanced the generic configuration to allow us to do this. Finally, in summary, just what I was trying to describe is the fact that welds do not lend themselves to a classic fatigue analysis process. We don't have detailed geometry. We don't have detailed materials. So what we do is go back in and use structural stress approaches inside of DesignLife to allow us to analyze those. And again, in DesignLife, we're using structural stresses from nodal forces and moments to allow us to do welds in shell meshes, and we're using structural stresses from through thickness integration to allow us to do the calculation in solid models. And one of the hallmarks is we've made it very, very simple to go off and do these, basically build these models and to present the information to DesignLife such that you don't have to go off and do a tremendous amount of pre-processing to feed you these methodologies. With that,